Hey there, folks, back here with what I think would be our last video here for our study of derivatives. I wanted to put one more out here and go a little further with something that may have come up in our classwork, but I haven't really formalized in our notes or here in these videos. So I do want to kind of go back into this topic one more time. And at the same time, what it's going to do is it's going to give us some technique for working with chain rule composites of functions. It's going to give us what we're going to look at here, a little bit of help when working with those implicit derivatives and differentiation. And it's also going to give us a little bit of help with what we might think of are cases for nested chain rule, right? When we look at some nested chain rule occurring. What I'm talking about is the case for implicit forms of derivatives, right? We consider an implicit form that we may have looked at already if you've studied at all logarithmic differentiation, right? Go back through that video that I've posted for logarithmic differentiation. We did make use of this derivative seen right here. The derivative with respect to x for the ln of f of x. And we had noted that in its implicit form, implicit because we don't have necessarily a function defining f of x. F is just some variable value we think of as being u in our result, right? It is equal to just the result, f prime of x divided by f of x. Where, yes, if we consider u to be equal to f of x, that does imply u prime is equal to f prime, and we can substitute in for f prime and f, u and u prime, and be able to say something like the derivative with respect to x for the ln of u, right? Where we can certainly see here on the left-hand side, our derivative and the variable in our logarithm are certainly the argument of our function are simply not matching, right? Our derivatives with respect to x, the variable in our derivative is u, and the result ends up becoming u prime divided by u, where we think about u being our function f of x and u prime being its derivative. Right? This is a bit more convenient form to pack away in terms of understanding as a derivative rule, as opposed to just the case for the ln of x. The derivative with respect to x for the ln of x is simply equal to 1 over x, and that only is a derivative rule for the ln of x. Any other rule or any other way we use it is really working it into other rules. Whereas we can actually develop that rule in the context of a chain rule, as we see here, right? Where we think about our argument of the ln function not being x, but actually being some function of f of x, which is more like what we might encounter as we work with this value in a derivative. For example, suppose we might say here u is equal to the sine of x. Well, that would imply that u prime of x equals the cosine of x. And if we want to think about then the derivative with respect to x for the ln of the sine of x, right, that is just going to be u prime divided by u. And maybe we should bring that down here just to highlight that. U prime divided by u, which is equal to the cosine x divided by the sine x, or this value given by the cotangent of x, right? Being able to state here that this derivative seen here, which maybe we should also highlight as we set all this up, fits this form for the derivative with respect to x being the derivative of the ln of u equal to u prime of u, right, results in this cosine x over sine x, or the cotangent of x, right, rather readily without having to spend too much time setting up a chain rule. The rule already sort of sets up the chain rule in the rule. All right. And one thing we ought to notice, right? It is certainly more useful than just the rule itself, right? The result, the derivative with respect to x for the ln of u equal to u prime divided by u, one might argue is far more useful than the ln of x derivative just equal to 1 over x, right? And one way that can be argued is by noting that this rule does apply, I should say, for the case when our function for u is equal to x, right? This is true for any f of x, whereas then we can include the case for u equaling x, where u prime would equal 1, and we could then see within the rule itself that the derivative with respect to x for the ln of u in this case, and maybe I should bring that over, right, is equal to u prime over u, which in this case, because u prime is just 1 and u is x, is our understood result, 1 over x. It's almost as if the rule we've learned, the derivative with respect to x for just the ln of x equaling 1 over x, is one unique case for a much more generic rule. And that would be the derivative with respect to the x for the ln of any other variable value that could be thought of as being related to x as a functional relationship. That always can be expressed as u prime divided by u for the ln of u. Now we can set this up not only for the ln of u, you could set this up for any of our other specific rules. Right? Specifically, if we maybe look at the case for the e to the x rule. Right? We do know the derivative with respect to x for e to the x is simply e to the x. Well, letting u equal f of x in that case implies that u prime would be equal to f prime of x. And if we thought about the derivative with respect to x for e to the u, that could be thought of as being u prime times e to the u. Right? Again, we might argue far more powerful rule to understand than just the specific case where u is equal to x, which would be the case that we developed initially with respect to just the derivative of e to the x. Right? Being familiar with this rule, we can find derivatives for composites of e to the u, right, where u is some function of f of x, right, some function f of x, some function of x, can be expressed simply as u prime times e to the u. We can do that for any of our functions here where we have specific cases, right? And I do go through a list of them here, and you can set some up for some that we haven't even really defined, perhaps, right? Like for instance, letting u equal f of x, u prime would equal f prime of x in these examples. And we could think of a derivative with respect to x for u to the n. Well, that would be n times u prime times u to the n minus 1 power, where n is any real number, right, not equal to 0. Right? We could see that case for the nth root of u. In the case for the derivative with respect to x for the nth root of u, we could show that that's equal to u prime over n times the nth root of u to the n minus 1 power. And this being true for any positive integer n greater than or equal to 2. For our square roots and beyond. All right. We can see this rule work itself into just our general exponential functions, such as b to the u. The derivative with respect to x for any base b at u, right? We might just say here, let's maybe point that out. This is where b is any base. B has to be greater than 0, and b b cannot equal the value of 1. All right. We can say this general rule. We can say this general rule not only for the case of an exponent of base b, we can say the same rule for the case of a logarithm of base b. A very similar looking rule. Where the derivative with respect to x for the log base b of u could be written as u prime over u ln of b. Again, where b is any base. All right. This rule can be presented in general for our 6 trig functions, as we see here. The derivative with respect to x for the sine of u is simply u prime cosine u, whereas the derivative with respect to cosine u is negative u prime sine u. The derivative with respect to x for the tangent of u is u prime secant squared u, whereas the derivative with respect to u for the cotangent of u is negative u prime cosecant squared u. Right? You can see how u prime works itself into each of these results as a factor. Other than that, it's the same derivative result we would see in the case of x. If we would go down here and replace this just with x, u prime would end up becoming the value of 1, and u would be the value of x. We'd be left with negative cosecant squared of x for the derivative with respect to x for the cotangent of x. But here we set it up in the context of u. Right? Where in the context of u, we do have to include that factor u prime in our result. All right? You can perform that for our trig functions, and you can say this all for our inverse trig results also. Right? The derivative with respect to x for the sine inverse of u is u prime over 1, the square root of 1 minus u squared. Very similar to the rule we saw for x, where if u was x, x prime would be 1, and our result would be 1 over the square root of 1 minus x squared, the result we had seen for the specific case of x. Now here, u is thought of as a function of x, and if u is a function of x, the result is u prime over the square root of 1 minus u squared, where again u is that function of x. And we can say that for each of our 6 inverse trig functions also. All right? Now, where I said this has some usefulness beyond these implicit results, because notice these are implicit results that we could apply in our implicit differentiation, or encounter in our implicit differentiation. We can also use this for nested chain rules. Here's a nested chain rule problem. Here you might say we have, 4 different functions being composed with each other. Maybe we say here this is like a 3-layer composition because we have 4 things being composed into, 3 layers, perhaps? Or is it really 4 layers? Maybe we count it as. I don't know. I think that's just how we want to look at it one way or another. But here we have several functions. We have the cosine function, which is being composed with the natural exponential function, which is being composed with, I'm going to make this just a little bit, highlight that a little bit more as a radical, as the square root of x squared plus 2x plus 1 is the exponent of that natural exponential function. So here we have a square root of x squared plus 2x plus 1 being composed with, e being composed with it, and then composed with the radical, we have inside there the quadratic, x squared plus 2x plus 1. This is several layers deep in its composition. 4 different function types: cosine, natural exponential, square root, and quadratic. We might be able to identify all of those cases. Now here, setting it up, letting u equal e to the square root of x squared plus 2x plus 1, ends up implying that my derivative with respect to x is just simply now the derivative with respect to x for the cosine of u, which we know from above is negative u sine u. And because u is equal to the square root of x squared plus 2x, or e to the square root of x squared plus 2x plus 1, we can substitute that back in to the sine function here for u. Right? U is equal to that. And we're left with finding u prime. Now, u prime is going to be the derivative with respect to x for this natural exponential function composed with the square root, which is composed with the quadratic. And in that, we can do another let statement. We can let v equal that radical of the quadratic. That ends up implying, when I think about the u prime in the previous statement, its derivative is equal to the derivative now with respect to x for e to the v, where that result from the rules above would be just equivalent to v prime e to the v. And because e to the v has v equal to this radical, the square root of x squared plus 2x plus 1, we're left with v prime times e to the square root of x squared plus 2x plus 1, replacing the v in e to the v with its value given by the radical. Now we're left with finding v prime. What is v prime? V prime is the derivative with respect to x for that radical. In that radical, we could declare a third variable to be the quadratic. We might let w equal the quadratic x squared plus 2x plus 1. And what that implies is that v prime then can be written as this derivative with respect to x for the square root of w. W being this function of x squared plus 2x plus 1. Where we know from the rules above for the square root function, this is equivalent to w prime over 2 times the square root of w. Again, w we know is the quadratic, x squared plus 2x plus 1. As for w prime, we're at the point where finding the derivative with respect to x for that quadratic falls upon some just fundamental rules for finding the derivatives of polynomials, which gives us 2x plus 2, which I might as well factor as 2 times the quantity x plus 1. Because you notice if I plug that above in for w prime, the 2's will end up canceling. Right? And maybe, don't say that, maybe I should at this point because it's not so clear later on. So maybe I should say here, so v prime then can be said to be equal to 2, let's say here 2 times the quantity x plus 1 over 2 square root of x squared plus 2x plus 1, where we will see those 2's cancel, leaving us with x plus 1 over that radical, the square root of x squared plus 2x plus 1. All right, so let's highlight that now. Come on. And then we'll say what I was going to say is that the derivative with respect to x for our initial derivative, which equals negative u prime sine e to the radical square root, or the radical of x squared plus 2x plus 1, where u prime, if we substitute in for that, we found above, that was negative v e to the square root of x squared plus 2x plus 1 sine e to the square root of x squared plus 2x plus 1. Where in the next step, we can substitute in for what we found for v prime, the statement above. Now, I am going to swap this out, and I'll say it this way. It seems kind of redundant to use the w prime here. We should maybe just say it this way. All right? Making this result above, where we can see those twos cancel. And then with that result, what we have really here are three numerators. This three factors in a numerator. That factor and this factor. 1, 2, and 3. We can put those in the numerator. Right? We have that negative out in front. All this is over this radical in the denominator. Right? And thus, I think I do make a thus statement here. Nope, not quite. Actually, I'm kind of redundant there with the canceling. So let me... I was trying to... I think I saved myself a step here by writing it the way we did. Where is it? Yeah, here's our thus statement. Thus... we can say the derivative with respect to x for the that should be cosine of e to the square root of x squared plus 2x plus 1 is equal to the opposite of x plus 1 times e to the square root of x squared plus 2x plus 1 times the sine of e to the square root of x squared plus 2x plus 1, all divided by the square root of x squared plus 2x plus 1. Right? We find this derivative calculation, this complex derivative calculation for this, case of a nested chain rule, right? Involving 4 functions, 4 layers, 3 to 4 layers deep, right? In a rather quick and painless manner. We're down the line here, right? We were just slowly decomposing our results, right, with a declaration of a variable in a composition in each case, right? Here we declared u as this, so we end up with the derivative with respect to x for the cosine of u, where we know that's negative u prime sine u. And we're left with finding u prime, this derivative here, where we declare that radical as another variable v, which leaves us with e to the v as our derivative, which we know is from above v prime e to the v. Here's where we're using those results from above to quickly be able to say this is v prime e to the square root of x squared plus 2x plus 1. Or when we think about then v prime being this derivative, we can declare a w to be the quadratic, and we're left with the derivative with respect to x for the square root of w, which becomes w prime over 2 square root of w from the results above, where we can then return that back to the statement for v prime, that is x minus 1 over this radical. And when we go back to our initial derivative calculation, we're able to, each step along the way, substitute in for those prime statements, right? The u prime gets substituted in for its value that involves v prime, where v prime gets substituted in for its value, where we've already pre-substituted in for w prime. Right? And then what you'll notice is this does give us a nice factored form in the end. Right? We do get a nice factored form from this in the end. Right? This is a little usefulness to these implicit forms of our derivatives. Right? We use that implicit formation here to draw this result quickly. We use that implicit formation here to draw this result quickly. And we use that implicit formation here initially to draw this result quickly. Right? All for finding the derivative of this complex nested chain rule. Right? All of our rules for specific cases of functions, algebraic functions, our trigs, our inverse trigs, our exponentials, our logarithmics, our powers, our radicals, right, can all be generalized to an implicit form where we involve u instead of x, where we think about u being some other function of x. Our result is then going to incorporate a factor of u prime, where that u prime then is the value we think of as being f prime of x. And this is somewhat of these are extremely more, we might think of more powerful results to kind of store away and remember for our derivative rules than just the generic results for the case of x themselves, or maybe I should say the simple cases where u is equal to x. All right. So, I think that is where I'm at with our derivative study here, folks. I do think at this point we're going to move over to some application in my notes here in my online lectures and in our coursework. So that is where we're heading, folks. And with that said and that done, that is quite an accomplishment in our study. And I think we did a pretty good job of trying to prove just about everything along the way. I think we did prove. Hopefully I gave enough proof of everything along the way, where I left very little what one might call mathematical magic. There was no mathematical magic there, folks. I always showed you what was up my sleeve when we were working with these derivatives and their calculations and their proofs. So, and all these rules that we've developed. So what we're going to come back to again then, I said, is a little bit of application. And I got some things to show you about how these are used, folks. Some useful application. So we'll continue with that in hopefully my next video here. I'll see you then.